Hello, people. Welcome to video number 3 of Improper Integrals. Before we go on, I guess I want to remind ourselves that whenever we were doing the definite integral, whenever we were doing this, we had two requirements that we had to meet, right? The interval had to be finite. So from A to B, we had to have a finite interval because we're finding the area in between a starting point and an ending point. And then the fundamental theorem of calculus said f had to be continuous if I was going to use the fundamental theorem. And so if the integral doesn't meet those requirements, this is why we're manipulating the situation here where we have to rewrite it somehow. And this certainly comes into play whenever I'm looking for the integral from negative infinity to positive infinity. Well, this infinite behavior means that we've now are wrecking havoc here because we're starting at negative infinity and we're going all the way to positive infinity, and we're looking for the area under the curve in between those infinite endpoints, right? And so what we're going to do is we're going to kind of change the situation so that we can use what we know, and then we could possibly get an answer. So whenever you have a situation where we're going from negative infinity to positive infinity, what we can do, because we know the properties of integrals say that I can pick a value in between those two. Now, there's an infinite number of values between negative infinity on the left side of the x-axis and positive infinity on the right side of the x-axis. So I'm going to choose a simple one like 0. So what I'm going to do is I'm going to break this integral up that says we're going to go from negative infinity to 0 of the function, and then we're going to add the integral from 0 to positive infinity, because if I have this function that's continuous, then this should be a nice break apart, right? So negative infinity to 0, and then from 0 to infinity means I'm going from negative infinity to 0. I'm sorry, from negative infinity to positive infinity. So now we can continue with our work here, which is we need to take a limit. In this case, we're taking the limit as, and I've been using t. I think most textbooks use b or a, but it really doesn't matter. And maybe we could use the 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 letter that we normally use for the bottom is a, and the letter that we usually use for the top limit is b. So why don't we use that? The limit as a approaches negative infinity of the integral from a to 0 of e to the x dx, plus the limit as b approaches infinity from 0 to b of e to the x dx. Okie dokie, let's see. Can we get an answer out of this? Well, can I find the antiderivative? The antiderivative of e to the x is e to the x, but I still need to evaluate that at 0 and a as I take my limit as a approaches negative infinity. Well, according to the fundamental theorem, I can substitute the top value minus the bottom value, remembering that I'm taking the limit as a approaches negative infinity. Okay. Well, if I can continue with this section before I start the other one, e to the 0 is 1 minus. Now I'm taking the limit as a approaches negative infinity. So I'm putting bigger and bigger negative values. How do I say that? I guess technically they're infinitely smaller values because they're more and more negative, right? So let me phrase it that way. As I put more and more negative values in here, like negative 100, negative 1,000, negative. I mean, this is becoming, just to kind of belabor the point here, we're doing things like this, right? Where my a is approaching negative infinity. But what does this mean? Well, this means that I have 1 over e to the 100, 1 over e to the 1,000, 1 over e to the 10,000. What's happening to these values? They're getting closer and closer to 0. So this goes to 0. So in this first part, I can say that I have an answer, right? It converges from a to 0. So now let's see if we can do the second part so we can add those two together. So I'm going to take the antiderivative again. This time I'm substituting b first, 0 on the bottom, and we're taking the limit as b approaches positive infinity. Well, that would be the limit as b approaches positive infinity of e to the b minus e to the 0. Well, e to the 0 again is 1, so that's good. But when I try to do the limit as b approaches positive infinity of e to the b, that means I'm putting bigger and bigger numbers here. My exponential is just growing without bound. So this is going towards positive infinity, and that means my limit doesn't exist. So as soon as one of the limits doesn't exist, it really doesn't matter if I put them together because the whole thing's going to fall apart, right? And so therefore, I can say that this improper integral actually diverges. However, if I had stopped at 0 and only gone from negative infinity to 0, that improper integral converged because we actually got an answer of 1. But by including the second half of the graph, and I say half, second half from 0 to positive infinity, that's going to go to positive infinity and it's going to diverge as a whole. This is how we can deal with infinity at both ends of my limits of integration. We can find a value in between and break it up into two pieces. Now, that's different than if I have an infinite discontinuity. So we know that an infinite discontinuity means there's a vertical asymptote. Let's spell it correctly here. Asymptote. So if there's a vertical asymptote at b, then b doesn't have to be infinity, right? B could be a value. It's just telling me there's a vertical asymptote at that value. And if that's the case, then we're going to say take the limit as t approaches b from a to t of f of x dx. So wherever the issue is, wherever the infinite issue is, whether it's in the form of an actual infinity endpoint, quote unquote, my limits are positive or negative infinity, or if it's an infinity because there's a vertical asymptote at a specific number, then I'm going to use the limit there. And then the same thing over here, we're going to take the limit as t approaches a from t to b of f of x dx. We're using the limit to deal with the infinite behavior that's occurring, either because I'm talking about the end behavior on the x-axis or because there's a vertical asymptote at a specific point. And that's going to be the case when I look at number 4. So this will be the last one we do for this video, but let's take a look at how this we can do this. I notice that I don't see any infinities in my integral. However, I now realize that if I substitute 0 wherever I see an x, I'm going to get a 0 in the denominator and a 2 in the numerator. That means there's a vertical asymptote. There's infinite behavior at x equals 0. So x equals 0 is the issue. So we're going to say, let's change this to the limit as a approaches 0 of the integral from a to 2 of this thing being this integral, or this integrand that I'm taking the integral of. So now I need to find the antiderivative. Then I'm going to plug in the top limit, plug in the bottom limit, subtract, and then take the limit as a approaches 0. Well, I noticed that this might require me to do a little u substitution. So I'm going to come over here, and I'm going to say, well, what if u is the inside of the square root? That means du is 2x plus 4 dx. Well, I don't have a 2x plus 4 dx. I have an x plus 2. But I just noticed that really this, if I double it, will give me 2x plus 4, which is what I need. But if I multiply that by 2, I got to balance it out with that on the outside. Okay. If that's the case, then that means I can rewrite this, and I'm going to switch colors in doing so. Let's go to this color. So now we're taking the limit as a approaches 0 of 1/2 of this whole thing is going to be replaced by du. And then the square root is still in the denominator, and this is going to be replaced by u. And while we're at it, we can also replace the top and the bottom limits, right? I can substitute this x value into the u formula, and I'll get 2 squared plus 4 times 2, which I believe is 12. And I can substitute the bottom limit into the formula, and I'll get a squared plus 4a. Okay, I think I got it. But now I need to find the antiderivative. By the way, this step is just so that we can find the antiderivative. Here's the other good news. I don't need to go back into the world of x's because I've switched everything, not only the integrand that I switch into the world of u's, but I've also switched these top and bottom limits of integration. Well, 1 over the square root of u is the same thing as, I'm just going to erase it here, u to the negative 1/2. Now I can take the antiderivative. That would be u to the positive 1/2 divided by positive 1/2. If I add 1 to the exponent, I get 1/2, and then I divide by 1/2. That's the same thing as multiplying by 2. However, don't forget, there's still a 1/2 in the front of the integral to the left. And also don't forget, we're taking the limit as a approaches 0. And I need to evaluate this at 12 and at a squared plus 4a. Where did this come from? Well, we substituted a into the u formula so that I can get things in terms of u, and that's what I got. If I'm multiplying by 2 and multiplying 1/2 times 2, these are going to reduce, right? So I'm just left with u to the 1/2. So just to clarify that, these reduce, and I'm left with 12 to the 1/2 minus the square root, because it's u to the 1/2, of a squared plus 4a. Well, if I take my a value, if I take my limit value that a is approaching, and I substitute it into my formula, that means I'm going to get 0. By the way, this 1/2 power, I guess I could have written it as the square root of 12. But if I substitute 0 in here and 0 in here, that whole thing goes to 0, so I have the square root of 0, 0, and therefore my final answer is this. This is a convergent improper integral. And that is how we attack improper integrals, by rewriting them using a limit in order to evaluate them.